Hello, let's talk about the state of the art in force and tactile sensing for minimally invasive surgery. Because the haptics perceptions play very important roles in surgery. It enables the surgeons to feel organic tissues handness, measure tissues properties, evaluate anatomical structures, and allows them to commit appropriate force control actions for steps for safe tissues manipulation. However, in minimally invasive surgery, the surgeon's abilities of perceiving valuable haptic information to surgery instruments is severely impaired. Performing the surgery without such sensory information could lead to increase of tissues trauma, and virtual organic tissue damage. In order to restore the surgeon's perspectual capability, methods of force and tactile sensing have been applied with attempt to develop instruments that can be used to detect issues, contact force, and generate haptic feedback to surgeon. The review the state of the art in force and tactile sensing technologies applied in minimally invasive surgery. Several sensing strategies, including displacement based, current based, pressure based, resistive based, capacitive based, piezoelectric based, vibration based, optical based sensing will be discussed. So this is related to force feedback, force sensor, haptic perceptions, minimally invasive surgery, or we normally call MIS, robotic surgery, tactile sensor. So MIS in operation performing surgery to small incisions with specially designed instruments and availing equipment known as endoscopic camera. Compared with open surgery, MIS is significant becoming the preferred approach since it offers distinct advantages of minimal invasiveness, including the reduction of intraoperative blood loss, tissue trauma, risk of post-operation infections, pain experiences with patient, and recovery time. Nevertheless, because the MIS operating field is not directly accessed, surgeons face many difficulties in performing the operation to limited vision and small keyholes. Laparoscopic procedures whereby surgical instruments are usually inserted into the patient's insuffered abdominal cavity, then require a relatively long training period from surgeons since the insertion point act like a fulcrum requiring them to cope with the rehearsal of their hand movements at the instrument tip. Such loss of intuitiveness in the usage of laparoscopic, lap, laparoscopic, isn't laparoscopic tools have been highlighted as a main disadvantage, leading to wrong movements, fatigue, premature tumor on the surgeon side. In addition, the capability of obtaining kinesthetics of force, kinesthetics of force, and tactile information, referred to as haptic perceptions, referred to as haptic perceptions, where the tissues interacting with the instrument is greatly impaired with frictions because friction between the instrument shaft and the insertion port, acquiring common tactile information to palpitations, as usually done using traditional surgeries. Therefore, it's not possible. So recently, robots in master-slave configurations, such as the SEUR surgical systems, and the Da Vinci surgical systems, have been introduced. We also know the Da Vinci surgery system have been introduced to solve motion constraint problem in MIS. As a consequence, dexterity of tool and tissue manipulator has been considerably augmented. This achievement facilitates surgeons to carry out a varieties of minimally invasive operations, more effectiveness, including prostatomy, which is removal of prostate gland, cellulitectomy, cololectomy is a specific word, mean removal of gallbladder, and cystectomy, which is removal of urinary bladder. For more complex surgical operations that are very difficult to be conducted using minimally invasive techniques, such as coronary artery bypass and mitral valve repair. Robotic surgery has become more a key technology enabling surgery to achieve much better outcomes. However, force and tactile information is still not available to the surgeon. The force applied to an organic tissues can only be estimated to virtual feedback by observing the deformations of the tissue. Such lack of sensing ability greatly limits effectiveness of operations and is considered a major downside of current robotic systems. In order to perform the surgery effectively, the surgeon should be able to feel hardness or tensions of tissues, measure the variations of their properties, and evaluate anatomical structures such as nerve, vessels, and ducts. Tumors buried under the tissue surface may not be discovered even if these advanced visual devices, but it could be detected by the simple sense of touch. Restoring and enhancing capability of tactile sensation using a touch sensory sensitive device are therefore very susceptible to perform tissue recognitions. For tissue manipulator retractions and discussions, kinesthetic sensories is particularly essential as to prevent the application of excessive force. As found in several experimental studies, performing such important tasks without force feedback could result in increasing tissue trauma and unintentional damage of healthy issue. An investigation of group at Harvard University has also shown the force feedback significantly improved the performance of robotic surgical systems. The reduction of tissue trauma and damage of sensitive structures such as arteries could be expected when the surgeon operates with aid of force feedback. The use of force and tactile feedback is now an active interdisciplinary research involving various science and engineering disciplines. Many research groups have intensively investigated several related issues, including stability and transparency. Some work on measuring these tissue properties has also become conducted with special, specially designed instruments such as indenting, grasping, and rolling devices. However, before its applications can be made practically in MAS, major issues concerning sensing information acquisitions and stable force reconstructions must be solved. This is focused on the state-of-the-art in sensing technologies, addressing particular issues and considerations with regard to MAS instruments design and describing existing methods of force and tactile sensing. To perform the surgery in minimal invasive manner, surgeons usually insert straight long tubes known as endoscopic or laparoscopic instruments to incisions of about 3 to 12 millimeters diameter. The motion of each instrument is considerably constrained by fulcrums at each insertion port, allowing only movement in 4 positions possible degree of freedom, which are insertion, pitch, yaw, and roll. Although this usually does not cause much difficulties when performing simple movements, it could be very difficult and time-consuming of the surgeon to carry out highly dexterous manipulation tasks like suturing and knot tying. Modern laparoscopic instruments such as endo-wrist instruments and Da Vinci surgical systems have articulate joint at the distal end of its shaft near the gripper, providing more degrees of dexterity to facilitate surgery. So, it was shown in the picture. However, because the endo-wrist and other commercial laparoscopic instruments pose no force sensing capability, the effectiveness is still limited. To solve problems due to the lack of force sensing ability, sensing elements must be integrated with the instruments. To solve the problem due to the lack of force sensing ability, sensing element must be integrated with the instruments. Size and complexity of such elements depend on the degrees of freedom required for the force measurement. For highly dexterous instrument, especially that of a robotic system, the measurement of force and torque in all 6 degrees of freedom might be most desirable, though not always required. A few degrees of freedom of force measurements would of fast surface would suffice for some specific applications. The placement of censoring, the placement, the placement of the censoring elements is also an important method that could greatly influence the quality of force measurement. Basically, there are at least four locations where the sensing elements might be placed. Show the four possible positions to place sensing elements. So just place a locate near at the actuation mechanism driving a joint. If a surgical instrument has active joint driven by some source of actuations, it is possible to measure force acting at the instrument tip by way of monitoring stress of the mechanical linkage or response of the actuator. Sensing force at a position that is far away from survey constrained locations could be effective done with an appropriate sensing strategy. However, because the effects of force are transferred to the sensing area through mechanical linkage, frictions, backlash, gravities, and inertia could distort the force values, causing errors in the measurement. If high measurement accuracy is needed, force should be sensed close to the place where they are generated to reduce any possible errors. Located on the instrument shaft outside the patient's body, because this part of the instrument need not to pass through the instrument insertion port. There is not much constraint with respect to the size and material sensing device used in this case. However, a sensing device placed at these positions is considerably subject to frictions and reaction force created at the instrument insertion port. The qualities of those could be much higher than the issue interaction force acting at the instrument tip. Measuring the force at this location without any mean of friction compensation is thus not practical. Because the sensories of issues, contact force measurements is reduced. Number 3 would be located on the instrument shaft inside the patient body. At this location, friction and reaction force generated at instrument insertion port do not affect measurements of the tissue's contact force. It is therefore considered as one of the most desirable places for locating sensing element. However, this location encounters several space limitations. Since this whole sensing device must pass through the insertion port, the dimensions of the instrument measured at this position is usually limited to only 12 mm in diameter, while facing such restrictions, inertia and actuation forces generated from the mechanics and drive assemblies, such as cables actuating distal articulated joint or gripper, could disturb the measurements of the tissue's interaction force. So, number four would be to place it and locate the instrument at the instrument tip, such as on gripper jaw. The instruments which are equipped with a gripper offer additional possibility of integrating force sensor in the gripper. The jaw is the place where force acting at the surgery instrument tip can be measured most directly. Frictions and other disturbance force generated from any moving mechanisms do not affect the measurements of the tissue contact force as much as that in other cases. Unfortunately, the jaw is a place that exhibits most severe space limitations. Only instruments which have either a large gripper or extremely small sensing elements can be considered for these cases. Considerate can be considered for these cases. For this case, another important issue that cannot be ignored in the design of sensing instruments is sterilizability. Sterilizability. For surgical instruments that are usually used inside human body, proper cleaning before they can be reused is essential in order to prevent infections. Precisely, stream sterilizations known as autoclave is standard method widely applied to sterilize surgical equipment. The sterilization method commonly employs saturated steam to heat the equipment up to 121 degrees Celsius at 103 kilopascal above the atmosphere pressure for at least 15 minutes. Such high temperature, such high temperature and pressure are required to ensure complete destructions of a microbial life form, including fungi, bacteria, and virus. Unfortunately, the intensive heat, pressure, and humidity can also potentially destroy sensors, electronics, and even installations of simple electric wires. For equipment which are not be able to withstand such humid, pressurized heating in autoclave, chemical sterilization protocol using chemical agents such as protodiethylamine, which is hydrogen peroxide, ethylene oxide gas, present an alternative. Ethylene oxide gas represents an alternative. However, chemical sterilizations requires much more time to ensure complete sterilization. Also, not all equipment is suitable to be sterilized due to limited penetratability and adverse effects of chemical agents. In most cases, stream sterilization is still considered most dependable and preferable. Equipment which cannot be sterilized by any of the sterilization methods could not be reused or need to be economically disposed of. So let's talk about sensing method. Displacement-based sensing is the number one. Number A, one of the simplest methods to sense force is to detect the displacement change of inelastic elements such as linear spring. Refers to the force displacement relationship described in the common physics law. A change in spring length indicates the magnitude of the overall force acting on it. A displacement sensor such as potentiometers, digital encoder, or linear variable differential transformer, or either device that can provide an accurate displacement measurements can be applied as a sensing element. If the stiffness of the spring is accurately known, the force the force value can be easily determined by a simple multiplications simple multiplications of the displacement and the stiffness. If not, estimate of the force value can be made by applying a calibration rule or more advanced spring model. One of the well-known force sensing devices that apply to the sensing principle is the LVDT-based force transducers. As name applied, the transducers make use of an LVTD to perform force measurement. With regard to this, the LTV LVTD core is usually coupled with a linear elastic element, where the force is applied at cause and cause the elastic element to deform. The position of the LVDT core will change, allowing analog signal to be generated in proportional to the applied force. This sensing scheme is capable of providing accurate measurements and can even resolve millinewton force. More advanced techniques estimate the use of real elastic elements. The more advanced techniques eliminate the use of real elastic elements, but simulate its characteristics in a servo system based on an approach well known in force feedback research. Techniques were developed by some researchers like Rosens to measure force in tele operation force reflecting endoscopic grab spur. According to the instrument design, the grabber's jaws are driven by a flat core actuator, which is a modified Hadis head precision device. This actuator is connected with high resolution position encoder and proportional derivative controller to form a servo control configurations. The proportional gain incorporated with an appropriate derivative gain of controller was set such that it effectively and efficiently simulate high mechanical stiffness characteristics. As usually required to ensure transparencies in force feedback systems. Thus, real mechanical elastic elements was not used, but the servo was applied to mimic its elastic behavior. A similar control architecture was also implemented in master hand control side. During operations, the position of the grab spur tips is compared with the reference input generated at the master hand control. If a difference, a position error is detected, as it is usually the case when the tissue is being grabbed, a grabbing force is automatically detected and reflected to the master hand control. Mechanical properties of the grabbed objects, such as tissue hardness, can also be felt. However, since the force is estimated from the difference of two displacement measurements, errors and the force estimations could rise in different such quantities was produced from other sources such as frictions at joints and backlash in dry mechanisms. Proper design, carefully assembly, and mean of compensate are. So proper design is carefully assembly, and mean of compensation are therefore substantial to reduce such unwanted effect. So number two, we call it B, current-based sensing. Another possibilities to measure force is to detect current of electric motors actuating. Another possibility to measure force is to detect the current of electric motor actuating a particular joint, like a motor actuating particular joints. If the joints are driven by servo control mechanisms, the values of torque or force generated by the servo motor can be determined since they are usually proportional to the armature current of the motor. Based on this principle, a force exerted on the motor axis could be considerable as a disturbance of the servo control system. An effort of the controller that attempt to increase the motor current, an effort of the controller that attempt to increase the motor current to produce sufficient force for balancing disturbance effects can be interpreted as the magnitude of the force being measured. So the effort of the controller that attempt increase the motor current to produce sufficient force for balancing disturbance can be interpreted as a magnitude of the force being measured. Yes, for an application in MAS, this sensing method was investigated by Trolley with a specially designed laparoscopic grab burst. A DC motor was used in this case to actuate the grab burst jaw, though a cable-driven mechanism. With a calibration rule, the grasping force was calculated from the amount of the current applied to the motor. Although this method offers a simple way for measuring the force, it does not provide very accurate measurements since the force usually is not directly measured. Its values is just estimate from the current of the motor, as found in several experiments. The actual force exerted at the instruments were somewhat smaller than those estimated from the current measurements. This could be due to the effects of friction at joints of all linkage and the initiator of involved mechanisms. Some of the motor currents were usually supplied for accelerating or moving elements, and thus cause a sort of overestimations. Other nonlinear effects generated from mechanical backlash, variations in the motor brush conductivities, and a change in armature winding resistance could also greatly degrade measurement ability. Appropriate calibrations, elaborate compensation, and advanced estimation techniques using disturbance observer or an extended common filter can help to increase accuracy of sensing scheme. But completely estimating all measurement error is difficult. This thus limits the usefulness of the current-based sensing surgery to applications where accurate sensing information is not required. Number 3 would be the pressure-based sensor. An alternative way to develop the force sensing device is to make use of pneumatics equipment, which described earlier. Forces can be measured in actuator-based approach using current sensing scheme, but in some cases the pneumatics actuators are used. It's also possible to detect force to measuring the pneumatic pressure. Recently, tornado have been developed for degree of freedom pneumatic driven forceps that pose force sensing capability. The forceps consists of 4 joints which are driven by wire rope power transmission mechanisms driven by several pneumatic actuators. In these systems, the delicate force sensing capability was constituted by introducing disturbance observer to pneumatic servo system. The information which is necessary for the estimations of the forceps contact forces, such as the differential pressures of the pneumatic cylinders, joint displacements, and joint velocities, are supplied to disturbance observer. Those are further preceded by an internal estimation protocol. The observer makes use of a neural network to estimate possible driving forces of all joints, which are then compared with the force estimate from measurements of the pneumatic cylinder pressures. The differences indicating the contact force low pass filter, so that the actual contact force at the forceps tip are effectively predicted. Since the effectiveness of the disturbance observer must depend on accuracy of the dynamic model of the forceps, the neural network was selected and trained to cope with the complex characteristics including nonlinearities, system uncertainty, and joint interference. But however, because the force measurements was carried out far away from the point that the force actually applied, backlash of the driving mechanisms, variation of frictions at joint, and those pneumatic cylinders themselves degrade estimation quality. Applying a well-trained neural network disturbance observer, applying a new trained neural network disturbance observer, and minimizing the source of inaccuracies using low frictions pneumatic cylinder with careful design drive assemblies, the sensing capability was significantly improved. Performance tests show that the forceps has good sensing ability, being capable of determining contact force values with a resolution as good as 0.1 Newton. So number 4, resistance-based sensing. In many applications, most of the force measuring device are strain gauge. Yes, many applications, most of the force measurement device use strain gauge as the sensing elements. To provide accurate means of force measurement, the strain gauge is usually bonded to flexible structures called fracture. When a flaw is called a strain in structure, The electrical resistance of the strain gauge will change, allowing the applied force to be electrically measured. However, because the underlying principle of the strain gauge measurements is based on the measurements of the structural deformations, there is always trade-off between the stiffness of the structure and sensitivities of the measurements. In robotic systems, for instance, high stiffness characteristics of structure is substantial for sustaining mechanical linkage. Working instruments and being manipulated, an object being manipulated. Unfortunately, stiff structures tend to provide low measurement sensitivity. A very stiff structure may almost not deflect even though a high force is applied. This thus causes difficulty in force measurement. Another phenomenon that restricts flexibility of the sensing device design is hysteresis. To prevent possible unwanted effects from such phenomena, monolithic flexure made of single piece of metal is usually exploited. In comparison, a sensing structures composed of several mechanical linkage could be could exhibit effects. Yes, this several in comparison, a sensing structure composed of several mechanical linkages could exhibit effects of frictions which cause hysteresis as a result. In MIS, developing a force sensing device is even more challenging since limitation its size greatly restrict the flexibility of sensing device design. At the University of Washington, strain gauges were applied to motorized endoscopic grasper, or we call it MEG, motorized endoscopic grasper, for measuring force and issue properties. They were placed in they were placed in a partial pulley, which was used as mechanisms to drive the instrument jaws. The pullays does not pass through the instrument insertion port, but is linked to the jaw at the in the instrument tip by linear translation linkage. A brushless DC motor equipped with a digital encoder was installed to motorize all these mechanisms. Although the instruments is mainly designed to help study biomedical characteristics of soft tissues in the laboratory. It is well-designed structures. It is well-designed structure also enable possibilities that could be practically applied in MAS. In fact, because the strain gauge, motors, and other electric components always lie outside abdominal cavities, so they need not to stabilize. Only the interchangeable laparoscopic instrument shaft is needed to be dismounted and autocave afterward. Since was developed, this instrument has been successfully used in many experiments to investigate characteristics of soft tissue in both in vitro and in induced conditions. However, because the sensing elements locate far away from issue interaction point, minimalize backlash and frictions of all joint is really important for preventing source of measurement inaccuracy. So to get rid of possible measurements errors, a robotics force feedback instrument developed at the Technical University of Munich. Yes, the robotics force feedback instruments developed at technology at the Technical Universities of Munich has stand gauge located at the instrument shaft close to the gripper. All strain gauges were arranged in diametrically opposed pairs to form two symmetric full bridge configurations around the instrument shaft. These configurations offer very sensitive force measurements in two directions perpendicular to the shaft axis with high signal-to-noise ratio and thermal effects cancellations. Although force acting along the shaft due to tissue punching and pulling actions cannot be detected. Yes, cannot be detected. So let's look at the picture right here. There would be some example possible locations for placing sensing elements. So there would be different way that we can put sensors on. Yes, we're talking about we test with the systems and then we will go to have a look at the example and picture about this. Yes, we talk about the robotics force feedback from Technical University of Munich. They test and they put the configurations which offer really sensitive force measurement in two directions perpendicular to the shaft axis with high signal-to-noise ratio, the thermal effects cancellations. Although force acting along the shaft used due to the tissue punching and pulling actions cannot be detected, the instrument have been intensively used to study important aspect of minimally invasive robotics surgery, MIRS, including autonomous surgical procedures, and the roles of the force feedback in robotic surgery. In developments of force sensing instruments based on strain gauge technology has been conducted at Johns Hopkins University. Yes, conduct at Johns Hopkins University. Recently, the researcher named Prasad have developed a 2 degree of freedom force sensing sleeve that can be investigated with a variety of 5mm laparoscopic instrument. and the full bridge strain gauge was also used in its sensing elements. They were placed on the shaft at the positions that is usually inserted through the insertion port. The steve, which is made of biocompatible materials, can measure a bending load of up to 10 Newton. It cannot be sterilized by a standard autoclave process, but it compatible with alternative stabilization protocol using ethylene oxide gas. Subsequent research at the university resulted in a 3 degree of freedom force sensing laparoscopic scraper. In the instrument, the strain gauges were placed right on the grasp jaw, just that in the highest possible sensitivities to direct manipulation force was obtained. A full and half Wheatstone bridge were introduced to a jaw to sense bending force in two perpendicular directions. A Poisson bridge. A Poisson's bridge, this is just the name of the circuit, was also adopted for sensing axial forces. Due to the space limitation, the Wheatstone bridge, the name, and the Preston bridge were placed on different grasp per jaws. So, strain gauge using strain gauge sensing also provides solution even more complex force measurement. At German's Aerospace Center, DLR, the researcher named Sobel have developed a digital force torque sensor for laparoscopic instrument. So in the picture, the sensors make use of a hexapod structure known as a strut platform to locate 6 strain gauges for measuring force and torque using all of the 6 measurement axes. Yes, by taking advantage of such special hexapod structures fabricated from a aluminum copper magnesium alloy, the sensor is achieve good measurement sensory with a very satisfactory structure stiffness characteristic. It can measure force with resolution of 0.25 newtons in axial directions and 0.05 newtons in radial direction. The measurement range could be as high as positive or negative 20 newtons to 200 newton millimeters for the force and torque measurements respectively. So it's 20 newton and 200 newton millimeter. The whole device has a diameter of 10 millimeter, which is acceptable for MIS. This is great. Rather than dealing with complex multi-axis force measurements, rather than dealing with complex multi-axis force measurement, the researcher named Mencia at the St. Anna School of Advanced Study of Pisa have developed a teleoperations microgripper which can measure interactions force of a small sample of tissues and processes micro vessels. This device employs a flexible joint-based deformable structure equipped with 4 semiconductor strain gauges to carry out force measurement during grasping. All strain gauges are arranged in a full width stone bridge configurations, enabling temperature effects to be minimized. The microgripper's structures is directly coupled with piezoelectric actuator, providing the capabilities to control the movement of the microgripper fingers to grab an object of interest. After carrying out proper calibrations with all components, the force sensing signal can be accurately read out with good sensitivity and linearity over measurement range of 0 to 6 millinewton. These measurement characteristics are very useful for performing delicate, minimally invasive operations. The researchers report that the device was successfully used to conduct various experiments, tissue properties, identifications, and microvessel palpations through a haptic interface. Yes, it's through a haptic interface. Although strain gauge has been extensively applied for developing various force sensing instruments, motor materials such as conduction polymers have also been introduced to contribute to the development of force sensing elements for MIS-2. These include a prototype of an MIS graph spur developed by a Scotex researcher, which employ a thin conductive polymer sheet placed over an array of 32 tiny spherical electrodes. The conductive polymer is covered by a copper foil and encapsulated with a top layer of silicon rubber. Since force exerts on the top layer cause change of the contact area on the electrode, the electrical resistance between the copper foil and the electrode change in proportion to the applied forces. Working in these fashions, its electrodes act as a resistance-based force sensing element. The combinations of all elements in the arrays can provide more information than other single-axis force sensors, since not only the magnitude of the applied forces, but also distributions of the forces perpendicular to the sensory surface can be determined. Recent advances in microelectromechanical systems, or MEMs, have been conducted to the development of miniaturized force sensing instruments such as a sensor integrated forceps and small cutting tool. In the industrial sections, the name Volumeter company, for instance, is one of active biomedical device manufacturers, have been conduct intensive research on applying a new microfabrication technique for creating small surgery device. Instead of constructing sensing elements and surgical tools separately, the company used the tool themselves as a substrate for semiconductor strain gauge fabrication. Robotics, microforceps, and surgical sharp with strain gauge embedded to their surface were then successfully developed on extremely small scale. This demonstrates the great potential of microfabrication technology in medical area, in particular for, say, miniaturized MIS capable smart device. Number 5, capacitive based sensing. Oh, among several sensing principles, capacitive sense-based sensing is known as one of the most powerful means of detecting extremely small defections of structures. For many applications, which require better performance than strain-gauge sensing can provide, capacitive sensing schemes represent alternative of offering a good sensitivities to very small deflections without this direct temperature dependence. So this is capacitive-based sensing. Ground baking work on micros. Ground baking. Groundbreaking work on microsensor development have conducted by Gray and Feller based on their research on capacitive sensor array at University of California, Berkeley. Miniature tactile. Yes, a miniature tactile. It's a minimal miniature miniature tactile array sensor for endoscopic tools was developed. The sensor array was fabricated using micro machining techniques consisting of egg by egg cells of capacitive sensing elements. The array, which is less than 1 square millimeters in size, is covered by a thin protective silicone rubber layer so as that force exerts onto the rubber's surface. Yes, force exerted onto the rubber surface spatially distributed on a mechanically low-pass filter. Deformations due to contact forces that cause change in capacitance of the sensing elements allow the force to be detected using oscillatory circuit. Its small size and ability to resolve millinewton force make the sensor attractive for developing small MAS devices such as for sensory surgery, surgical manipulators, and yes, surgical manipulator and catheters. Based on the capacitance measurement principle, our researcher at the Harvard University have developed a remote palpation system which was intentionally designed for helping the surgeon to search. Yes, for helping the surgeons to search for hidden arteries and tumor. Yes, help the surgeons to search for hidden artery and tumor buried inside tissue during MIS procedures. The sensing component of the system is a capacitive tactile. A capacitive tactile array sensor made of two cross layers of copper strips. All of these separated by a thin strip of silicone rubber, which a force is exerted above the cross strip structure. The distance between the copper strip will decrease, causing change of capacitive values. The capacitance change measured at all crossing points were then used to determine spatial spatial determine spatially distributed set of forces with a possible resolution of as good as 0.001 Newton over a measurement range of 2 Newton. The entire tactile array sensors was placed on a handheld laparoscopic palpation instrument, allowing the surgeons to press the sensors against the surface area of interest with specially designed electronics and computer-based signal processing systems. Various forms of delicate palpation information, such as variations in pulsatile such a variation in pulsatile pressure in artery stiffness and textures of soft tissues could be read out and conveyed to surgeon by either a visual or intuitive tactile display. Tactile sensations is important for most type of surgeries, since it allows surgeons to detect organic structures, including those which are hidden inside the tissues, rather than measuring a single net force. Many tactile sensors are capable for detecting spatially distributed force over that sensing surface. This capabilities enables the sensor to gather a great deal of organic palpation information, including variations in shape and hardness. A varieties of techniques and materials have been used with attempts to produce tactile sensors that are sensitive, reliable, rugged, small, and low cost, capacitive based tactile sensors are some of these pose such capabilities. However, the utilization of such sensors is usually limited for applications that require precise measurements over a small range. Number 6. Piezoelectric based sensing. Piezoelectric materials have been considered as potentially effective sensing elements in tactile sensors. If well fabricated, they are able to provide several advantages over other type of sensing devices. For instance, they can sensitively generate voltage when their structures are deformed due to compressions. Although an extremely small deformation is caused by a small punching force, a large output voltage can be generated. The capability to produce voltage distinguishes piezoelectric sensors from most other sensors, since no electrical power is needed to be supplied to the sensing elements. The operations are considered considerable, very reliable, and application range is greater than with other sensors. One of the many piezoelectric material is the polymer polyvinylidene. Yes, polyvinylidene fluoride, referred as either PVDF, PVF2, polyvinylidene. It is one of the most well-known materials used for constructing thin sheet tactile sensors. For an application in MAS, DAGI applied material in the development of micro-machined tactile sensor that can be equipped with a jaw of endoscopic grasper. The sensing elements, PVDF film, was attached with a number of patented aluminum electrodes. They all were placed between a rigid tooth like silicon structure and a flat plexiglass substance. It's a plexiglass substrate plate. For a prototype sensor, 4 electrodes were placed right under the teeth of the silicon structure. When a force caused stretch in the PVDF film, polarization change with produced voltage signals are generated. The magnitude, positions, and disturbance of the applied force can then be determined by measuring the amplitude of the voltage. Measuring the amplitude of the output voltage at all electrodes and comparing such quantities among them. This sensor exhibits very high sensitivities and good linearity. High signal-to-noise ratio over measurement range of 2 Newton was also achieved with this design. Subsequent research on PVDF-based, tactile-based sensors lead to a novel sensing structure design that can simultaneously measure the magnitude of the applied force. The locations is distribution. The location of the force is distributions, and additional the issue softness. The researcher proposed a design of an MAS grasper. Okay. Yes, for an MAS grasper, which each sensor unit comprises 3 PVDF film. One is attached to a flexible beam, and 2 are located on both of these end supports. So in the big picture illustrates such a sensing configurations. The force applied on the beam can be measured by the PVDF film, and is supported while the softness of an object being grasped can be quantified from the beam defect detected by the PVDF film attached to the beam. Other research on tactile sensor development using piezoelectric materials has also been performed by Otomo. Instead of using PVDF, ferroperm piezoceramics was selected since it is considered to be suitable for MAS applications due to its distinctive characteristic. Yes, due to its distinctive characteristics such as high charge coefficients, low temperature coefficients, and high Curie-name temperature. Breaking through this temperature can result in loss of piezoelectric sensitivity. Several piezoelectric elements were arranged in 3x10 array pattern and covered by a protective layer made from silicon rubber. The whole array was designed for measuring tissue, palpations, force up to 15 Newton. Small size, low cost make it well attractive for MAS applications that require low mounting space and dispository. is by smelting space and disposability. Although many piezoelectric-based sensors offer variety advantages, it is important to note that piezoelectric materials are inherently subject to shock leakage. Yes, inherently subject to shard leakage, which cause deteriorations, deteriorations. Oh, yes, which cause deteriorations, deteriorations. Yes, which can cause deteriorations of voltage and or diff in the presence of static forces. This characteristics makes piezoelectric sensors only sensitive to time-varying force quantities. For applications that require detection of static force, piezoelectric sensor would not provide true measurement. Another drawback is concerning the properties that yes is a phenomenon. It's called pyroelectrics, 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 electric, pyroelectrics of properties of the piezoelectric materials. Tactile sensors made from piezoelectric elements could be very sensitive to change in temperature without an effect mean of protections or compensations. The abilities to obtain accurate tactile information from this type of sensor could be limited. Yes, the seventh one, vibration-based sensors. Instead of relying on the detection of forces using passive force sensing element, some tactile sensors are capable for obtaining tactile information through dynamic response. This refers to the development of the so-called miniaturized vibrotactile sensor that can be used to measure the dynamics mechanical properties of soft tissues, including dynamical stiffness during MAS. At Fraunhofer Institute for Biomedical Engineering in Germany, a vibrotactile sensor prototype was designed comprising an alternate current AC excitation coil which generate an oscillations magnetic field to induce vibrations on permanent magnet. The magnet, which is attached with elastomer membrane located at the tip of the sensor head, can vibrate within range of 100 to 800 Hz. The amplitude phase and frequency of the vibrations are accurately measured by using an eddy current sensing scheme. This involves the use of additional components, including conducting displays on permanent magnet and measurement coil located nearby. When the vibrations is activated, the conduction disc, magnet, and elastomer membrane will start to oscillate at resonance frequencies. The eddy currents induced in the conducting disc cause cyclic change of the electrical impedance of measurement coil, allowing the amplitude, phase, and frequency of the oscillation movement to be measured. The resonance frequency as well as the phase and amplitude will change When the sensor comes into contact with a sample of soft tissues, due to its uh, viscous elastic properties, damping the harmonic oscillations, the information concerning mechanical properties of tissue stiffness. Since the resonance frequency of the sensor in contact with the tissues tend to increase with increasing tissue stiffness. In the research, a prototype of the Vibro's tactile sensors was used to examine various human tissues. The results showed that the sensor can help differentiation between healthy and unhealthy tissues, such as healthy mucosa. Oh, this is a technical word. Carcinoma, tumorous undermine mucosa. However, to find the resonance frequency at each measurement, the sensor needs to take several seconds to scan throughout the whole frequency range. To perform faster measurement, a vibrating tactile sensors which make use of a piezo transducer were developed in research. The transducer, which is made of lead ceramics, is a zirconate barium titanate ceramics, pulse a resonance frequency of as high as 92 kilohertz. When the sensor gets into contact with tissues, its resonance frequency will shift to a new value. The difference between the resonance frequencies under different conditions can then be detected using a vibration detector. Look at it inside the sensor head. Immediately after frequency difference is detected, the piezoelectric transducer adapts its oscillation to change a resonance frequency. Applying such a feedback system running at a high frequency excitation permits to the sensor to evaluate tissue stiffness very rapidly without scanning over the whole frequency range. This thus allows the real-time identification of the mechanical property of soft tissues to be performed. Yes. Number 8. Optical based sensing. The first attempt of using optical sensing strategy is was proposed by Hirosh and Yonida. It was subsequently applied in various applications in robotics and medicine. Applying on optical sensing scheme is an alternative way to measure force and transfer force information. Instead of using electrical wires to carry electrical signals, fiber optic cables are used as a medium to carry force information from sensing region to optoelectrical equipment. A sensor which applies an optical sensing scheme using optical fiber is also known as optical fiber sensors. The fundamental component of an optical fiber's for sensors are a light source, a transduction element, also known as modulator, and an optical detector. The light source generates light that travels to the transduction element through a light transmitting optical fiber. The transduction elements modulate the light in proportion to the values of the force being measured. The modulated light then travels to receiving optical fiber to optical detector. After the light reaches the detector, it is convenient into electrical signal and further propelled by electronics equipment. Generally, the optical detector consists of a photodiode and signal conditioning circuitry. Okay. Circuitry that can amplify the electrical signal produced by photodiode. The light source could be a light emitted diode or LED, a laser, or even a halogen lamp. Most often, LED are utilized since they are reliable, widely available, and inexpensive. In cases where high optical power output is required, laser and halogen lamps are employed. The sensing methods that are usually applied to fiber optic sensors can be classified in two major categories known as S known as extensis and intensis. In extensis sensors, the optical fibers serve as transmitter mediums to deliver a light signal from the light source to the transduction element and from transduction element to the detector. In this case, most of the modulations of the light signal take place at the transduction element. Differently, in intensive sensor, the light modulations occurs inside the fiber itself. A measure variables such as force or pressure deform the fiber. The pressure deform the fiber, causing its conductivity to change, and therefore the light traveling in it is modulated. Besides the extensis, and intensive light intentions modulations, advanced modulation techniques based on the phase and spectrums of the light beam also available. Okay. Yes, also available. In an extensive modulated sensor, the intensities of the light beam traveling through an optical fiber is modified by effect of measured variables in transduction regions. This can be determined in proportional to light intensity detections and optical detectors. According to this, a refractive intensive modulated mechanism can be used to modify the light intensity. And these sensing mechanisms make use of reflectors to deliver light transmit from the transmitting optical fiber to the optical detectors. The intensity of the light can be used to change the distance between the reflector and the fiber tip. As the distance decreases, increased amount of the light proportional to the distance are captured by receiving fiber. In practice, a coupler it's often used to couple. In practice, yes, the coupler is often used to couple the transmitting and receiving light into single fiber. A portion of light transmitted through the transmitting fiber can also be provided as a reference for the photoelectric signal processing. Apart from this benefit, the use of copper also offers a good configuration for the light intensity measurement, since only a single fiber is wired to the sensing element. Sensor distortion due to misalignment between the fiber is eliminated. As the Leuven University, the researcher have utilized configurations in 5mm diameter force sensors for minimally invasive robotic surgery (MIRS) applications. Three optical fiber sensors were employed to measure deformations of flexible titanium alloy structures mounted on a surgery instrument shaft. The force measurement corresponded to change the distance between a reflective surface and all three fiber arranged at 120 degree intervals. All three fiber will detect the same displacement change when only axial force are applied. If there an radial force exerted at the instrument tip, different displacement change will be detected on resultant and the resultant radial force component can be computed. This sensing configuration offered excellent force measurements in 3x with resolutions of 0.04 Newton and lengths of 2.5 Newton in actual directionals and in an actual directions and 1.7 Newton in the radial directions. The force itself is completely electrical, isolated from other electronics, and therefore completely immune to electromagnetic interference. Another advantage of using optical fiber sensors is magnetic resonance (MR) compatibilities. In medicine, magnetic resonance imaging (MRI) has been widely used to investigate living organs, exploiting the advantage of MRI providing high quality image non-invasively. A number of MRI guided robots have also been developed. For MRI guided robot to operate in MR environments, there are several constraints in deploying conventional mechanicals and electronics instruments. On the one hand, ferromagnetics materials in metal part of the robotics instrument could degrade magnetic field homogeneously. Yes, the field homogeneity of homogeneity of the MR system causing distortions of the MR image. On the other hand, strong magnetic fields and radio frequency RF pulse necessary for producing MRI images could induce noise in the employed sensor systems, degrading the sensor output. Electrical wires are not suitable for use in MR environments since they usually induce eddy currents and magnetic fields, disturbing the MRI signal. However, such robotic systems for sensing information would be essential. Unfortunately, most force sensors containing electrical components cannot be employed in MR environments. Sensing force to optical fiber is one of the only field methods that can be practically applied at the University of Calgary. For example, an MR compatible Yes, an MR-compatible embedded sticks robot known as NeuroArm have been developed for minimally invasive neu- neurosurgery. Yeah, the robot makes use of an optical fiber force sensor to measure two interaction force in three axes on each of ends effectors. In this case, the force information is captured by means of detecting reflected light signal traveling through optical fibers probes. This information is then used to generate haptic force feedback, allowing the surgeon to perform complex microsurgery effectively on human brain. Although optical fibers have great potential for sensing instrument development, there are limitations in utilizing such materials, particularly in intensive in intensities modulate sensors, where measurements principle relies on measurements of the light intensity. The measurement's accuracy could be degraded if the light signal is uttered outside. Yes, if the signal is uttered outside the transduction regions, such as outside the fiber cables, and near their connections due to bending and misalignments. Thus, means of preventing or compensations, such as using reference fiber, have to be incorporated. Also, many types of optical fiber are not as flexible as electric wires. They are easily damaged and usually require precise interface with other system components. Small fiber bending can cause signal attenuations and fluctuations, which can be compensated for, while large bending can lead to damage to fiber core. So, in MSI surgeons, so in the MSI surgeons lose almost complete their abilities perceiving tissue contact force to surgical instrument. Performing surgery without perceiving such important sensory information greatly limit the ability of the surgeons to minimize tissue damage and trauma. In order to enhance the surgeon's perspectual capabilities, the instruments that are capable for capturing and delivers force information to the surgeons are needed. The several techniques of force sensing have been already employed based on their suitabilities of specific applications. Among those sensing principles, displacement-based sensing seems to be the simplest way to measure force. It allows measuring the magnitude of force over a wide range, but its usefulness is usually limited to the measurements of force in only one of few directions. Current-based sensing and pressure-based sensing offer two possible to detect force through the current of the motor and pneumatics pressure respectively. Yeah, sorry, pneumatic. Motor and pneumatic pressure respectively. Eliminations of specific force sensors is advantage of those sensing scheme, but good measurement accuracy is difficult to obtain since the forces are not directly measured. Frictions, backlash, gravity, and inertia of mechanical linkage could greatly degrade the quality of the force measurement. For cases where high accuracy is required, a direct force measurement scheme using strain gauge, for example, is preferable. Recently, emerging technologies in the area of microfabrications have demonstrated possibilities not only to detect single net force but also to measure spatially distributions of force. Capacitive-based piezoelectric-based sensors are usually utilized for such measurements since they offer outstanding characteristics in resolving extremely small force despite their small size. Modern resistive-based and vibration-based sensors have also made their contributions in different ways for acquiring tactile information. However, there are limitations in employing electronic sensing devices in MIS, especially in cases where electronics isolation and immunity of electromagnetic interference is required. Yes, it's required to capture force information in those server environments, including in this workspace of MRI machine and optical-based sensing scheme. Using optical fiber is one of the only field methods that can be applied. Force and tactile sensing instrument development is an active research involving several disciplines of science and engineering. Many research groups have intensively investigated related issues, and much research is currently undertaken. However, before a sensing instrument can be practically applied in MIS, major obstacles concerning hardware design, signal processing, surgical system integration, and human-machine interface must be overcome.